Quantum energy is one of those phrases that can sound mysterious before it has even had a chance to explain itself. It suggests something hidden, something restless, something quietly woven into the world beneath tables, stars, atoms, and empty space. But in real physics, quantum energy is not magic, not a secret fuel, and not a strange glowing substance waiting to be bottled. It is something much more interesting than that. It is the way nature measures, exchanges, stores, and transforms energy when reality is examined at its smallest and deepest levels. Welcome to the Late Lab. It's lovely to have you here. Before we settle in properly, it would be wonderful to know where you're watching from tonight. Maybe you're tucked up in bed with the lights low, resting on the sofa after a long day, listening through headphones while the house goes quiet, or half awake somewhere between curiosity and sleep. Wherever you happen to be, I hope you're warm, comfortable, and able to let the day loosen its grip for a while. If you enjoy these calm little journeys through science, leaving a like and subscribing is a simple way to help the channel keep drifting along. And if you're already subscribed, thank you. Truly, it means a great deal and it helps more than you might imagine. Tonight's subject is the hidden quantum energy beneath reality, which sounds dramatic enough to make the universe put on a tiny lab coat and look suspiciously pleased with itself. But the real story is quieter, stranger, and far more beautiful. It begins with light, heat, atoms, fields, and the surprising discovery that energy, deep down, does not always behave like a smooth-flowing stream. Sometimes it arrives in steps, sometimes it appears in allowed levels, sometimes even empty space refuses to be completely empty. So let's begin, gently. What is quantum energy, really? And how can something so hidden help shape almost everything you see? The phrase quantum energy has acquired a strange little fog around it. It sounds as though it should mean a shimmering force hidden inside crystals, or a secret cosmic battery humming behind the wallpaper of the universe. It has been borrowed by adverts, wellness trends, science fiction, and the occasional person on the internet who seems very confident beside a suspiciously expensive bracelet. But in real physics, quantum energy means something far more precise, far more measurable, and in many ways far more remarkable. It does not refer to a mystical fluid. It is not an invisible glow that can be scooped out of the air. It is not a special kind of energy separate from ordinary physics. Quantum energy is simply energy described under the rules of quantum theory, where matter and light behave in ways that are deeply real, experimentally tested, and often unlike anything familiar from everyday life. To understand why this matters, it helps to begin with energy itself, because energy is one of the most important ideas in all of science, and also one of the easiest to misunderstand. In ordinary speech, energy often means alertness, mood, excitement, or the heroic decision to get off the sofa after sitting down for exactly 3 minutes. In physics, energy has a stricter meaning. It is a conserved quantity associated with motion, position, heat, mass, radiation, particles, fields, and change. Energy is not a material thing drifting around like dust in sunlight. It is a way of accounting for what physical systems can do, how they transform, and how one kind of activity can become another. A moving object has kinetic energy because of its motion. A stone held above the ground has gravitational potential energy because of its position in Earth's gravitational field. A hot cup of tea contains thermal energy because the atoms and molecules inside it are jostling about more vigorously than those in a colder object. Light carries energy as electromagnetic radiation. Matter contains energy through mass itself. Chemical bonds store energy because atoms and electrons are arranged in particular ways. Fields can hold energy too, even when no solid object is sitting there looking important. The great beauty of physics is that all these forms can be linked. A falling stone converts gravitational potential energy into kinetic energy. A burning candle transforms chemical energy into heat and light. A steam engine turns thermal energy into motion with a level of drama that 19th century industry found very appealing. A star converts nuclear energy into radiation, sending light across space for years, centuries, or billions of years before it reaches an eye, a telescope, or a sleepy viewer trying to relax while learning about the foundations of reality. The idea that energy is conserved emerged gradually. Gottfried Wilhelm Leibniz, in the late 17th century, argued for a quantity related to motion that he called living force. Émilie du Châtelet later helped clarify and defend ideas about motion and energy, including the importance of the square of velocity in measuring the energy of moving bodies. James Prescott Joule, in the 19th century, showed through careful experiments that mechanical work and heat are related, famously linking motion, temperature, and the mechanical equivalent of heat. Hermann von Helmholtz then helped express the broader principle of conservation of energy, stating that energy can change form, but the total amount in an isolated system remains constant. That idea is still central to modern physics. Energy conservation is not just a handy rule for steam engines and falling apples. It appears across mechanics, electromagnetism, thermodynamics, relativity, quantum mechanics, and particle physics. In the 20th century, Emmy Noether revealed a deeper connection between conservation laws and symmetries. In simple terms, the conservation of energy is linked to the fact that the laws of physics do not change from one moment to the next. Time passes, clocks tick, tea cools, stars burn, and yet the underlying rules remain consistent. That consistency has consequences. Quantum theory did not throw energy conservation away. It changed the way energy behaves at small scales. In the classical world, energy often seems smooth. A rolling ball can slow down gradually. A planet can orbit with continuous motion. A spring can be stretched a little, then a little more, then a tiny bit more after that. Classical physics often allows energy to vary in a continuous way, as though nature uses an infinitely smooth dimmer switch. But at the quantum level, the universe often behaves less like a smooth dimmer switch and more like a staircase. Energy can be exchanged in discrete amounts. An atom does not usually absorb just any amount of light. It absorbs particular amounts that match the difference between allowed energy levels. An electron bound inside an atom cannot simply settle into every possible energy value. It occupies states permitted by quantum rules. Light itself, once treated only as a wave, can also behave as packets called photons, each carrying an amount of energy connected to its frequency. This is where quantum energy becomes genuinely strange, without needing any mystical decoration. The strangeness is not that energy becomes magical. The strangeness is that nature appears to count. At tiny scales, many systems have allowed energy states, forbidden gaps, wave-like behavior, probability, and uncertainty woven into their structure. Energy is still energy, but the bookkeeping is no longer smooth and familiar. It has steps, thresholds, and patterns. This discovery began with Max Planck's work on blackbody radiation in 1900, when he proposed that energy was exchanged in small units to solve a problem involving heat and light. Albert Einstein took the idea further in 1905 when he explained the photoelectric effect using light quanta, later called photons. Niels Bohr used quantist energy levels to explain features of the hydrogen atom. Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and many others helped build quantum mechanics into one of the most successful scientific theories ever created. From there, the idea deepened even further. Quantum energy is not only about particles jumping between atomic levels, it is also about fields. Modern quantum field theory describes particles as excitations of underlying fields. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. The Higgs field helps explain why certain fundamental particles have mass. The quantum vacuum is not simple emptiness, but the lowest energy state of fields that fill space. Even the phrase empty space begins to sound less empty once quantum theory has been allowed into the room, quietly rearranging the furniture. This does not mean the vacuum is a limitless power source, or that reality is secretly waiting to hand out free energy like a confused vending machine. Conservation laws still matter, thermodynamics still matters, experiments still matter. The real story is subtler and stronger. Beneath familiar objects, beneath chemistry, beneath starlight, beneath the mass of matter and the glow of the cosmos, there are quantum rules governing how energy can exist, shift, appear, disappear into another form, and shape the universe without ever becoming visible in the ordinary sense. So the hidden quantum energy beneath reality is not a fantasy force. It is the measured, structured, deeply tested behavior of energy in the quantum world. It is found in photons of light, in the allowed states of atoms, in the bonds of molecules, in the electronic bands of solids, in nuclear reactions, in quantum fields, in the vacuum, and perhaps in the deepest unresolved questions of cosmology. And that is much more interesting than magic, because it actually has to be true. Before quantum theory unsettled the furniture, the world of energy seemed wonderfully smooth. It was the world of rolling balls, swinging pendulums, turning mill wheels, falling rain, warm fires, stretched springs, and planets travelling through space in graceful curves. It was a world where change appeared to happen gradually, where motion could speed up or slow down by tiny amounts, and where nature seemed to behave like a well-made clock, assuming the clock had not been assembled by someone in a hurry after losing 3 important screws. This classical picture was not foolish. It was powerful, elegant, and astonishingly successful. It explained why stones fall, why cannonballs follow curved paths, why tides rise and fall, why machines work, and why planets do not simply wander off into the darkness like distracted sheep. In the everyday world, energy seems to move and transform continuously. A rolling ball does not usually vanish from one speed and reappear at another. It slows smoothly as friction steals some of its motion. A candle does not release its stored chemical energy in one neat, dramatic flash, unless something has gone badly wrong. It burns steadily, turning wax and oxygen into heat, light, and gases. The familiar world feels like a world of gentle transitions. One of the simplest forms of energy is kinetic energy, the energy of motion. A moving train has kinetic energy. So does a thrown stone, a spinning bicycle wheel, a flowing river, or a drifting cloud, though the cloud is less likely to cause trouble unless it has plans involving rain. The faster something moves, and the more mass it has, the more kinetic energy it carries. This is why a slow pebble and a fast train do not feel equally persuasive if they bump into something. Motion matters, and mass matters too. Potential energy is a little quieter. It is energy connected with position, arrangement, or stored possibility. A stone held above the ground has gravitational potential energy because Earth's gravity can pull it downward. A stretched spring has elastic potential energy because it is deformed and ready to snap back. Water held behind a dam has gravitational potential energy because it can flow downward, turn turbines, and become electricity. A log contains chemical potential energy because its atoms are arranged in ways that can release heat and light when it burns. Potential energy is not always doing something obvious, but it is waiting in the arrangement of things. Classical physics became the great language for describing these transformations. Isaac Newton's laws of motion, published in the late 17th century, gave physics a framework for connecting force, mass, and acceleration. His law of universal gravitation showed that the same kind of reasoning could describe both an apple falling toward Earth and the moon falling endlessly around Earth in orbit. This was a stunning unification. The heavens and the ground were no longer separate realms with separate rules. They were part of the same mechanical universe. In Newtonian mechanics, if the forces acting on an object are known, its motion can be predicted. A planet, a pendulum, a falling stone, or a sliding block can be described through continuous change. Speed can increase gradually, position can shift smoothly, energy can move between kinetic and potential forms as though passing from one cup to another, with no strange missing steps in between. A pendulum, for example, has more gravitational potential energy at the top of its swing and more kinetic energy at the bottom. Back and forth it goes, trading height for speed and speed for height, like a very patient demonstration that has been repeating itself for centuries. This classical view also treated energy as something that could vary by any amount. In principle, a rolling ball could have one speed, or a slightly lower speed, or a still slightly lower speed, with no smallest permitted step between them. A planet could orbit with a continuous range of possible energies. A spring could be stretched smoothly from barely at all to considerably more, right up until the spring decided it had tolerated enough. The underlying assumption was that nature's dials could be turned with perfect smoothness. That assumption worked beautifully for large objects. It still does. Engineers, astronomers and physicists continue to use classical mechanics because it remains extremely accurate in the right setting. Bridges, rockets, gears, engines, satellites and sports balls do not usually need the full strangeness of quantum theory to describe their motion. The classical world is not wrong so much as incomplete. It is a magnificent approximation, one that becomes clearer when the objects involved are large, warm, slow compared with light, and made from enormous numbers of atoms. But hidden beneath that smooth world was a problem waiting quietly. When physicists began examining heat, light, atoms, and the inner structure of matter, nature stopped behaving like an infinitely adjustable dial. Energy did not always slide gently from one value to another. In certain microscopic systems, it appeared in allowed amounts. Atoms absorbed and emitted light in precise patterns. Electrons occupied particular energy levels. Light itself could arrive in packets. The classical world had shown energy as a flowing landscape. Quantum theory would reveal staircases hidden inside it. The smooth classical world worked beautifully for falling stones, turning wheels, swinging pendulums, and planets moving through the dark. But physics does not only have to explain things that move from place to place, it also has to explain things that glow. A warm piece of metal gives off a dull red light. A hotter piece of metal glows orange, then yellow, then white. A bed of coals shines in the fireplace. A filament inside an old light bulb brightens when electricity heats it. The sun floods space with light because its surface is thousands of degrees hot, and deeper inside, nuclear fusion keeps pouring energy outward. Heat and light are closely connected, and for a long time that connection looked as though it should fit comfortably inside classical physics. But hot objects carried a quiet problem. When an object is heated, it emits electromagnetic radiation. Some of that radiation is visible light if the object becomes hot enough, but much of it may be infrared radiation, which is felt as warmth rather than seen by the eye. Even a human body gives off infrared radiation because it has a temperature above absolute zero. The room around you is softly glowing in infrared right now, though human eyes are not built to see it. Fortunately, this saves everyone from looking like a walking thermal ghost in the middle of the supermarket. Physicists wanted to understand this glow with precision. One idealized version of the problem was called blackbody radiation. A blackbody is not simply a black object in the ordinary sense. It is an ideal object that absorbs all radiation falling on it, and then emits radiation according to its temperature. Real objects only approximate this behavior, but the idea was extremely useful. If physics could explain the pattern of light emitted by an ideal hot object, it would reveal something deep about the relationship between heat, energy, and radiation. The pattern was clear from experiment. Cooler objects emitted mostly lower energy radiation, such as infrared. As an object grew hotter, the peak of its radiation shifted towards shorter wavelengths and higher frequencies. This is why heated iron can glow red, then brighter orange, then yellowish-white as its temperature rises. Stars behave in a similar way. Cooler red stars glow more strongly toward the red and infrared parts of the spectrum, while hotter blue-white stars emit more of their light at higher frequencies. Colour in this case is a clue to temperature. Classical physics tried to explain this using the known ideas of electromagnetism and thermodynamics. James Clerk Maxwell had already shown that light is an electromagnetic wave. Ludwig Boltzmann and others had helped build statistical mechanics, connecting heat to the motion and distribution of particles. Everything seemed ready, the ingredients looked respectable, the mathematics wore a clean jacket and arrived on time. Then the prediction went wrong. According to classical reasoning, a blackbody should emit more and more energy at higher and higher frequencies. At the ultraviolet end of the spectrum and beyond, the predicted energy became absurdly large. It suggested that hot objects should pour out enormous amounts of high-frequency radiation. This did not happen. Glowing coals did not flood the room with lethal ultraviolet light. Heated metal did not behave like an impossible energy fountain. Stars did not follow the classical prediction either. The real universe, once again, had declined to fill in the form correctly. This failure became known as the ultraviolet catastrophe. The name sounds dramatic, as if physics had accidentally opened a cupboard and found a very angry violet dragon inside. But the catastrophe was not an explosion in nature. It was a disaster in the theory. Classical physics predicted something that observation clearly did not support. The smooth old picture of energy had led to a result that could not be true. Max Planck approached this problem in 1900. He was not trying to make physics strange for the fun of it. He was trying to solve a very specific puzzle: how to describe the observed spectrum of blackbody radiation. Planck found a formula that matched the experimental data beautifully, but the formula required a peculiar assumption. The energy exchanged between matter and radiation could not take any possible value. It had to be emitted or absorbed in small discrete packets. These packets were connected to the frequency of the radiation. Higher frequency radiation came in larger packets of energy. Lower frequency radiation came in smaller packets. Planck introduced a constant that linked frequency to energy, now known as Planck's constant. It is an extremely small number, which is why quantum effects are usually hidden in ordinary life. But at the scale of atoms, light and heat radiation, it becomes essential. Planck called these small units energy quanta. The word quantum simply means an amount, but in physics, it came to mean something revolutionary. The smallest discrete packet involved in a particular physical exchange. Energy was not always transferred like water poured smoothly from a jug. In some situations, it was passed along like coins, beads, or steps on a staircase. The staircase could be incredibly fine, too small to notice in everyday life, but it was there. Planck himself did not immediately treat this as a complete overthrow of classical physics. In many ways, he saw it as a mathematical solution to a stubborn problem. The full meaning would take time to unfold. Albert Einstein would later use the quantum idea to explain the photoelectric effect, arguing that light itself could behave as if it came in packets. Niels Bohr would apply quantized energy to the atom. Quantum mechanics would eventually grow from the small, reluctant crack in the old wall. The glow of hot objects had revealed that the classical world was not the whole story. Heat and light, two of the most familiar things in existence, were quietly pointing toward a hidden structure beneath reality. Energy at its deepest levels did not always move as a smooth stream. Sometimes it arrived in portions. Sometimes nature counted. Planck's constant is one of the quiet little numbers that change the entire shape of physics. It does not sound very dramatic at first. It is not as visually grand as a galaxy, not as thunderous as a supernova, and not as easy to picture as a falling apple. Yet this tiny constant marks the scale, where the universe begins to reveal its quantum character. It is the small dividing line between the smooth world humans easily notice and the stepped, patterned, strangely selective world hidden underneath. In ordinary life, change appears continuous. A lamp can be dimmed gradually. A car can speed up smoothly. A cup of tea can cool little by little, from pleasantly hot to tragically forgotten. If energy changed only in visible quantum steps at human scales, the world would look very different. A thrown ball might speed up in jerks. Warmth might leave your hands in sudden chunks. Music might climb from note to note without the smoothness of sliding pitch. But everyday objects are made of enormous numbers of particles, and their quantum steps are usually far too small and tangled together to notice directly. Planck's constant helps explain why. It is the number that links the energy of radiation to its frequency. In clear terms, frequency means how rapidly a wave repeats. Blue light has a higher frequency than red light, and ultraviolet light has a higher frequency still. According to Planck's quantum idea, higher frequency radiation carries larger packets of energy. Lower frequency radiation carries smaller packets. The relationship can be spoken simply as the energy of a photon equals Planck's constant multiplied by the frequency of the light. That sentence is one of the doorway ideas of quantum physics. It means light does not always exchange energy as a perfectly smooth stream. It can behave as though it comes in little packets, later called photons. A photon of red light carries less energy than a photon of blue light. A photon of ultraviolet radiation carries more energy than either. This is one reason ultraviolet light can damage skin and chemical bonds more easily than visible red light. It is not simply that ultraviolet light is brighter in the everyday sense. Each photon carries more energy because its frequency is higher. Planck's constant is incredibly small. That is why quantum effects do not usually announce themselves in the kitchen, the garden, or the queue at the post office. The number is so tiny compared with ordinary human-scale energies that the steps blur into apparent smoothness. It is a little like looking at a staircase from so far away that it appears to be a ramp. Up close, the steps are real. From a distance, they merge into a slope. The classical world is often that distant view. Quantum physics is what becomes visible when the steps are examined closely enough. This also helps correct a common misunderstanding. The quantum world is not important because it is weak, vague, or delicate in the sense of being unreal. It is hidden because its effects are usually averaged across huge numbers of particles and interactions. A single atom can have sharply defined energy levels. A single photon can carry a specific packet of energy. But a warm object contains vast numbers of atoms vibrating, rotating, colliding, emitting, and absorbing energy all at once. The individual quantum actions are still there, but together they create the smooth-looking behavior of heat, colour, pressure, and motion. Imagine a beach made of countless grains of sand. From far away it looks like one continuous pale surface. Walk closer, and the surface becomes a collection of individual grains. The beach did not suddenly become grainy when someone noticed it. It was grainy all along. In a similar way, energy exchange at small scales can have a graininess that is invisible from the perspective of ordinary life. Planck's constant tells physics how fine that grain is. This was the great surprise hidden inside Max Planck's work on blackbody radiation in 1900. He was trying to explain the glow of hot objects, not launch reality into philosophical mischief. Yet his solution required energy to be exchanged in discrete amounts. That idea did not merely fix a technical problem, it opened a route toward quantum theory. Albert Einstein would later apply the idea to light itself. Niels Bohr would apply quantist energy to atoms. Erwin Schrödinger and Werner Heisenberg would help reveal a deeper mathematical structure behind these strange restrictions. Planck's constant now appears across modern physics. It is central to atomic spectra, quantum mechanics, photons, matter waves, electron orbitals, quantum field theory, and the deepest attempts to understand space, time, and gravity. Whenever the quantum nature of reality becomes unavoidable, Planck's constant is usually somewhere nearby, small but insistent, like a quiet signature written into the foundations, so the smallest step is not a tiny magical spark hiding in matter. It is a measure of how nature exchanges energy. When the scale becomes fine enough, it shows why light comes in packets, why atoms have allowed energy levels, and why the smooth world of experience is built from something more structured underneath. The hidden quantum energy beneath reality is hidden not because it is imaginary, but because its steps are almost unimaginably small, and yet from those steps come the colours of stars, the stability of atoms, the chemistry of life, and the strange precision of the world beneath the world. Albert Einstein is often remembered for relativity, curved space-time, and that famous hair that seemed to understand the universe better than most textbooks. But one of his most important contributions to quantum physics came from a quieter mystery, involving light, metal, and tiny escaping electrons. In 1905, the same extraordinary year in which Einstein published papers on special relativity and Brownian motion, he also offered an explanation for the photoelectric effect. It was a simple-looking phenomenon with very strange consequences. The photoelectric effect happens when light shines on a metal surface and causes electrons to be released. At first, this might not sound especially shocking. Light carries energy, electrons are held inside metal, and enough incoming energy might be expected to knock some of them loose. Classical wave theory seemed ready to handle the matter. If light were only a wave, then brighter light should carry more energy, and enough brightness should eventually push electrons out of the metal, regardless of the light's colour or frequency. A dim light might take longer. A bright light should work better. That was the comfortable expectation. But experiments told a different story. Heinrich Hertz first noticed the basic effect in the late 19th century while studying electromagnetic waves. Philipp Lenard later investigated it more carefully and found something deeply awkward for classical physics. The release of electrons depended not simply on the brightness of the light, but on its frequency. High-frequency light, such as ultraviolet light, could knock electrons out of certain metals even when the light was quite dim. Lower-frequency light, such as red light, might fail to release electrons no matter how bright it became. It was as if the metal did not care how much low-frequency light arrived in total. It cared whether each individual arrival carried enough energy. This was not how a smooth classical wave was supposed to behave. If light energy was spread continuously across the wave, then increasing the brightness should eventually provide enough energy for an electron to escape. The electron might need to gather energy for a little while, like someone slowly collecting coins to buy a train ticket. But that was not what happened. If the frequency was too low, no electrons came out. The light could be brighter and brighter, and still the electrons remained where they were, apparently unimpressed. Einstein took Max Planck's quantum idea and made a bold step. Planck had introduced energy quanta to explain blackbody radiation, but Einstein suggested that light itself could behave as if it arrived in individual packets of energy. These packets were later called photons. Each photon carried an amount of energy linked to the light's frequency. A higher frequency photon carried more energy. A lower frequency photon carried less. The key idea can be spoken very simply. The energy of a photon equals Planck's constant multiplied by the frequency of the light. This explained the photoelectric effect beautifully. An electron in the metal needed a certain minimum amount of energy to escape, called the work function. If a single photon had enough energy, the electron could absorb that photon and leave the metal. If the photon did not have enough energy, the electron stayed trapped. Adding more low-frequency photons did not help an individual electron escape, because each photon still arrived with too little energy. It was a little like trying to open a heavy door with 1,000 tiny taps when what the latch actually needs is one firm push. The quantity matters, but the size of each packet matters too. Brightness still played a role, but in a different way. Brighter light meant more photons arriving each second. If those photons had high enough frequency, more brightness could release more electrons, but brightness alone could not compensate for photons whose individual energy was too low, This distinction was the clue. Energy was not merely spread smoothly across the light wave, it was being delivered in quantum-sized portions. This idea was uncomfortable for many physicists because light had already been shown to behave like a wave. Thomas Young's double-slit experiment had demonstrated interference, a wave-like pattern that seemed hard to reconcile with little packets. James Clerk Maxwell's theory of electromagnetism had described light as an electromagnetic wave with magnificent success. Einstein was not simply replacing waves with particles. He was pointing towards something stranger. Light could show wave-like behavior in some experiments and particle-like behavior in others. Robert Millikan later tested Einstein's photoelectric equation with great precision. Interestingly, Millikan was not initially eager to accept Einstein's interpretation, but his experiment strongly confirmed the mathematical relationship between frequency and electron energy. Physics is good at this sort of awkward honesty. Sometimes an experiment pats a theory on the shoulder, while the experimenter is still frowning at it. The photon idea eventually became central to quantum theory. A photon is the quantum of the electromagnetic field. It carries energy and momentum, and it is responsible for the particle-like behavior of light. Yet light does not become an ordinary tiny pebble flying through space. It remains quantum, capable of interference, probability, and behavior that refuses to fit neatly into everyday categories. Photons are not distant curiosities. They are part of ordinary modern life. In solar panels, photons from the sun transfer energy to electrons in a semiconductor, helping generate electric current. In digital cameras, photons strike sensors and are converted into electronic signals that become images. In lasers, photons are produced in a highly organized way, creating light that is coherent and precise enough for fiber optic communication, barcode scanners, surgery, and laboratory measurements. In the eye, photons trigger chemical changes in light-sensitive molecules inside the retina, beginning the chain of events that becomes vision. Every color you see is connected to photon energy. Red light, green light, blue light, infrared radiation, ultraviolet radiation, radio waves, and X-rays are all forms of electromagnetic radiation, differing mainly in frequency and wavelength. Their photons carry different amounts of energy. This is why X-rays can pass through soft tissue and affect atoms more strongly, while radio waves can travel through walls without rearranging your bones, which is considerate of them. Einstein's explanation of the photoelectric effect showed that quantum energy was not just a mathematical trick used to fix the glow of hot objects. It was built into light itself. Energy could arrive in packets. The size of each packet mattered, and the old idea of perfectly smooth radiation had to give way to a deeper, stranger, more accurate picture. The hidden quantum energy beneath reality was no longer only hidden in furnaces and glowing metal. It was in sunlight, starlight, screens, cameras, lasers, and the quiet act of seeing the room around you. Every photon was a tiny reminder that light, one of the most familiar things in existence, carries within it one of the first great surprises of the quantum world. Once light had revealed its quantum nature, the same strange pattern appeared inside matter itself. Atoms, which had once seemed like tiny solid building blocks, turned out to have their own hidden architecture. They were not little billiard balls. They were structured systems, with a dense central nucleus and electrons arranged around it according to rules that classical physics could not explain. The problem was simple to state, and surprisingly difficult to solve. If electrons were negatively charged particles moving around a positively charged nucleus, why did they not simply spiral inward? In classical electromagnetism, an accelerating charged particle should radiate energy. An electron orbiting a nucleus would be constantly changing direction, which means it should lose energy, fall inward, and collapse into the nucleus almost instantly. If that were true, atoms would not be stable. Matter would not hold its shape. Tables, stones, oceans, bodies, and mildly judgmental houseplants would all have a serious structural problem, but atoms are stable, they do not collapse. They form elements, molecules, minerals, gases, cells, and stars. Something in nature was preventing electrons from taking every possible path and every possible energy. Niels Bohr offered an early answer in 1913. His model of the atom was not the final picture, but it was a remarkable step. Bohr suggested that electrons in a hydrogen atom could occupy only certain allowed orbits, each with a specific energy. An electron could not simply circle the nucleus at any distance with any energy it liked. It had permitted states, like rungs on a ladder. Between those rungs there were no stable places to stand. This idea helped explain a long-standing mystery, the spectral lines of hydrogen. When hydrogen gas is excited, it does not emit every colour of light smoothly. It emits light at particular wavelengths, forming a pattern of bright lines. Johannes Balmer had found a mathematical pattern in some of these visible hydrogen lines in the 19th century, though the deeper reason behind the pattern was not yet clear. Bohr's model offered that reason. The lines appeared because electrons were moving between allowed energy levels. When an electron drops from a higher energy level to a lower one, the atom releases a photon. The photon carries away the exact energy difference between those two levels. When an electron absorbs a photon with just the right energy, it can jump to a higher level. If the photon does not match the required energy difference, the atom may not absorb it in that way. Once again, nature was not behaving like a smooth ramp. It was behaving like a staircase. The spoken version of the key idea is simple. The energy of the emitted or absorbed photon equals the difference between the two atomic energy levels. This is the foundation of emission and absorption spectra. An emission spectrum is produced when atoms release light at specific wavelengths. An absorption spectrum appears when atoms absorb particular wavelengths from light passing through them, leaving dark lines in an otherwise continuous spectrum. These lines are not random, they are fingerprints. Each element has its own pattern because each type of atom has its own arrangement of energy levels. Joseph von Fraunhofer observed dark lines in the spectrum of sunlight in the early 19th century. Later, scientists realized that these lines revealed the chemical composition of the sun's atmosphere and other stars. This was an extraordinary discovery. Without touching a star, without bottling a piece of it, without sending anyone there with a clipboard and a very brave hat, scientists could identify elements across space by reading the missing and glowing colours in starlight. That is one of the great powers of quantum energy. It turns light into information. The pattern of photons absorbed or emitted by atoms allows astronomers to detect hydrogen, helium, sodium, calcium, iron, and many other elements in stars' nebulae. It allows chemistry to identify substances in laboratories. It helps reveal temperatures, densities, magnetic fields, and motions. When a star's spectral lines shift slightly toward red or blue, astronomers can measure whether it is moving away or toward us. Hidden atomic energy levels become messages stretched across the universe. Bohr's model was eventually replaced by full quantum mechanics. Electrons are not now understood as tiny planets orbiting the nucleus in neat circular paths. That image is useful historically, but it is incomplete. Modern quantum mechanics describes electrons using wave functions and orbitals, regions of probability shaped by energy, angular momentum, and the rules of quantum theory. Erwin Schrödinger, Werner Heisenberg, Max Born, Wolfgang Pauli and others helped build this deeper picture. Even so, Bohr's central insight remains essential. Atoms have discrete energy levels. Electrons bound inside atoms do not possess just any energy. They occupy allowed states, and transitions between those states involve photons with specific energies. The details became more sophisticated, but the staircase remained. This staircase is part of why matter exists in stable forms. If electrons could lose energy without limit, atoms would collapse. If electrons could occupy all the same states without restriction, the structure of the periodic table would disappear. Quantum rules, including discrete energy levels and the Pauli exclusion principle, help create the layered arrangement of electrons around nuclei. That arrangement allows chemical bonds, molecular shapes, solid materials, liquids, gases, DNA, proteins, and the soft machinery of life. The architecture of matter is therefore not built only from tiny pieces, it is built from allowed energies. The hidden quantum energy beneath reality is not merely something atoms contain. It is part of what gives atoms their identity, their stability, and their ability to join together into the world. The idea that matter might behave like a wave sounds, at first, like a category error. Waves are things that spread, ripple, interfere, and overlap. Particles are things that seem local, definite, and point-like. A pebble does not usually drift through a pond as a wave while also being the pebble. It would be an ambitious pebble, and possibly quite irritating to describe. Yet in the early 20th century, quantum physics began to show that light was not the only thing with a double nature. Light, which had long been understood as a wave, could also behave as if it arrived in packets called photons. Louis de Broglie then made a bold suggestion in the 1920s. If waves such as light could behave like particles, perhaps particles such as electrons could also behave like waves. This was the matter wave idea. De Broglie proposed that every moving particle has a wavelength associated with it, linked to its momentum. Momentum is the quantity connected with mass and motion. In simple terms, a faster particle, or a particle with more mass, has a shorter associated wavelength. For everyday objects, that wavelength is fantastically tiny, far too small to notice. A tennis ball, a cup, or a sleepy cat wandering across the room technically has a de Broglie wavelength, but it is so absurdly small compared with the object itself that it has no visible effect. The cat remains mercifully cat-shaped. For electrons, however, the matter wave becomes important. Electrons are light enough that their wave-like behavior can show up in experiments. In 1927, Clinton Davison and Lester Germer observed electrons scattering from a nickel crystal in a pattern that confirmed their wave nature. George Paget Thompson also demonstrated electron diffraction. These experiments showed that electrons could produce interference, a classic wave behavior. Matter itself had begun to ripple. Erwin Schrödinger took de Broglie's idea and developed wave mechanics. Instead of describing an electron as a tiny planet following a neat path around the atomic nucleus, Schrödinger described quantum systems using a wave function. The wave function is not a simple physical wave like a water wave or a sound wave. It is a mathematical object that contains information about the possible outcomes of measurements. Max Born later gave the wave function its probability interpretation, showing that it helps predict where a particle is likely to be found, or what value a property such as energy might have. This changed the picture of atomic structure. Electrons were no longer treated as little beads travelling around fixed tracks. They were described by wave-like patterns around the nucleus. These patterns could be stable or unstable, allowed or not allowed. The electron did not need to spiral into the nucleus because it was not moving like a classical charged planet. It occupied quantum states, shaped by wave behaviour and governed by precise mathematical rules. Werner Heisenberg added another essential piece with the uncertainty principle. This principle is often described as the idea that measurement disturbs what is being measured, but that is only part of the story and can be misleading. The uncertainty principle is deeper than clumsy instruments. It says that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision at the same time. This limitation is built into the structure of quantum systems. It is not simply that the measuring device is too rough, as though physics has been trying to use a ruler made of soup. The uncertainty principle arises because quantum objects are described by wave-like states. A wave with a very well-defined wavelength has a clear momentum, but it tends to be spread out in space. A wave squeezed into a narrow region requires a mixture of wavelengths, which means its momentum becomes less definite. The trade-off is not a failure of human cleverness. It is part of how quantum reality works. Energy in quantum mechanics is deeply connected to allowed wave patterns. A helpful comparison is a vibrating string, such as a guitar string. A string fixed at both ends cannot vibrate in just any pattern. It supports certain stable modes. These are the tones and harmonics the string can naturally produce. The exact details are different in quantum mechanics, but the idea is useful. When a particle is confined, its wave-like behavior must fit the space available. Only certain patterns fit properly, and those patterns correspond to certain allowed energies. The particle in a box is a simple conceptual example. Imagine a particle trapped inside a tiny region, unable to escape. Because it behaves like a wave, its wave pattern must fit inside the box. Some patterns fit neatly, others do not. As a result, the particle cannot have just any energy. It has a set of allowed energy levels. Even in its lowest state, it still has some energy, because a completely motionless, perfectly pinned down particle would violate the uncertainty principle. Quantum confinement itself creates structure. This is not just a classroom curiosity. The same broad principle helps explain atoms. Electrons are confined by their attraction to the atomic nucleus, and their wave-like states form particular patterns. These patterns become orbitals, not little circular tracks, but regions and shapes associated with different energies and probabilities. The allowed electron states give atoms their structure. That structure gives elements their chemical behavior. Chemistry then builds minerals, oceans, atmospheres, cells, and everything soft, solid, glowing, fragrant, edible, poisonous, or regrettably sticky. The energy of possibility is therefore not vague imagination. It is probability shaped by real physical rules. Quantum systems do not simply wander through every possibility in a casual dream. Their possible states are constrained by wave functions, boundary conditions, conservation laws, and interactions. The result is a universe where matter is stable not because electrons behave like miniature planets, but because they behave like quantum waves with allowed energies. The hidden architecture beneath matter is wave-like, probabilistic, and precise. It is not less real because it is strange. It is the reason atoms can exist without collapsing, the reason light can reveal their structure, and the reason the solid world can rise from patterns too small to see. Chemistry can feel like a science of substances: salt, water, oxygen, sugar, iron, gold, carbon, and all the tiny rearrangements that make one material behave differently from another. But beneath the names of elements and compounds, chemistry is really a story about electrons. More precisely, it is a story about where electrons are allowed to be, what energies they are allowed to have, and how atoms become more stable when those electrons settle into particular arrangements. That means chemistry is quantum from the beginning. It is not quantum in the decorative sense, as if molecules are wearing a mysterious little cloak. It is quantum because atoms bond by arranging electrons into allowed states around atomic nuclei. The shapes of molecules, the colours of minerals, the reactions inside cells, the hardness of diamond, the softness of graphite, the smell of rain on warm ground, and the fact that oxygen can be breathed while chlorine is best treated with extreme social distance all depend on quantum rules. Electrons in atoms occupy orbitals, which are not tiny circular tracks like planets around the sun. They are regions described by quantum mechanics, connected with probability, energy, and the wave-like behavior of electrons. Each orbital has a particular energy and shape. When atoms interact, their orbitals can overlap, combine, and rearrange, allowing electrons to be shared or transferred. These changes create chemical bonds. A crucial rule behind this structure is the Pauli exclusion principle, named after Wolfgang Pauli. It says that no two electrons in the same atom can occupy exactly the same quantum state. In simpler terms, electrons cannot all pile into the lowest possible state as if the atom were offering one very comfortable sofa and everyone had decided to sit on it at once. There are limits. Electrons must fill available states according to quantum rules. This principle is one of the reasons matter has structure. Without the Pauli exclusion principle, electrons would collapse into the lowest energy arrangement, and the layered architecture of atoms would disappear. The periodic table would not have its familiar order. Chemistry would not behave as it does. Atoms would lose the distinct outer electron patterns that make one element reactive, another stable, another metallic, and another essential for life. Electron shells and orbitals produce the deep structure behind the periodic table. The periodic table itself was arranged by Dmitri Mendeleev in the 19th century, before the full quantum explanation existed. Mendeleev noticed that when elements were ordered by their properties and atomic weights, patterns repeated. Some elements behaved like chemical relatives. Sodium, potassium, and lithium reacted in similar ways. Fluorine, chlorine, bromine, and iodine formed another family. Mendeleev even left gaps where he predicted undiscovered elements should belong, and some of those predictions turned out remarkably well. Quantum theory later explained why those patterns existed. Elements in the same column of the periodic table often have similar outer electron arrangements. Those outer electrons, sometimes called valence electrons, largely determine how atoms bond and react. Carbon has 4 outer electrons available for bonding in a way that allows it to form chains, rings, sheets, cages, proteins, fats, sugars, DNA, and a slightly alarming number of things that humans have managed to turn into packaging. Oxygen has a different outer structure, making it highly important in water, rocks, air, combustion, and respiration. Iron's electron structure gives it magnetic and chemical properties that matter in geology, technology, and blood. Gold's behaviour, including its colour and resistance to corrosion, also traces back to the quantum behaviour of electrons, with relativity playing a subtle role in its distinctive appearance. A molecule forms when atoms settle into a more stable arrangement together than they would have separately. That stability is about energy. In a covalent bond, atoms share electrons, and the combined arrangement can have lower energy than isolated atoms. In an ionic bond, electrons are transferred more strongly from one atom to another, creating charged ions that attract. In metallic bonding, electrons can spread through a structure, helping metals conduct electricity and bend rather than shatter. The details vary, but the principle remains. Chemical bonds involve energy differences, electron arrangements, and quantum states. This is why chemistry is not just a set of recipes. It is the visible behaviour of invisible rules. A molecule's shape affects how it interacts with other molecules. Water bends into a particular shape because of its electron arrangement, giving it polar properties that make it an extraordinary solvent. Proteins fold because atoms and molecules seek lower energy arrangements through electromagnetic interactions. Hydrogen bonds, water effects, and quantum-based chemical structure. Pigments absorb certain photons and reflect others, because their electrons have energy differences that match particular wavelengths of light. Colour, taste, smell, hardness, flexibility, acidity, and reactivity all emerge from this hidden arrangement. Biology depends on the same foundation. The energy stored in chemical bonds powers cells. Photosynthesis captures photon energy and stores it in molecular form. Respiration releases energy from molecules in controlled steps. Enzymes work by helping reactions follow lower energy pathways. DNA stores information in a molecule whose structure depends on chemical bonding. Life is not separate from quantum energy. It is built from chemistry, and chemistry is built from quantum states. So the hidden quantum energy beneath reality is not only found in particle accelerators, glowing laboratories, or equations written by people who drink heroic amounts of coffee. It is in salt dissolving in water. It is in the oxygen entering the lungs. It is in the carbon compounds of skin, leaves, wood, bread, and ink. It is inside every solid object, every breath of air, and every living cell. Matter feels solid and ordinary because quantum energy levels are quietly doing their work. The world is familiar on the surface because, underneath, electrons obey strange and precise rules. A single atom already has a hidden quantum structure. A molecule adds another layer, with electrons shared, shifted, pulled, and arranged into bonds. But when many atoms gather into a solid, something even richer begins to happen. The allowed energies of individual atoms do not simply remain separate and lonely. They spread, overlap, and combine into vast patterns called energy bands. This is one of the reasons a diamond is transparent. Copper conducts electricity, silicon can become a computer chip, and rubber stubbornly refuses to behave like a copper wire, no matter how politely it is asked. The properties of solids are not determined only by what atoms they contain. They are also determined by how electrons are allowed to move through the repeated structure of the material. In a crystal, atoms are arranged in a regular pattern. This repeating structure affects the wave-like behavior of electrons. Instead of having only isolated energy levels, as in a single atom, electrons in a solid can occupy ranges of allowed energies. These ranges are the energy bands. Between some bands, there are forbidden ranges, where electrons cannot normally have energies. These forbidden ranges are called band gaps. The band gap is one of the most important ideas in solid-state physics. It helps explain whether a material behaves as a conductor, an insulator, or a semiconductor. A conductor, such as copper or aluminium, has available electron states that allow electrons to move easily through the material. This is why metals can carry electric current. The electrons are not simply sprinting freely like tiny athletes down a polished corridor, but the quantum structure of the metal gives them accessible states through which motion can occur. An insulator, such as glass, rubber, or dry wood, has a much larger energy gap between filled states and available higher states. Electrons are effectively stuck in place under ordinary conditions. They cannot easily move into the states needed to carry current. This is why an electric wire needs a conducting metal inside and insulating material outside. One part invites electrons to move, the other part politely blocks them from wandering into your fingers, which is one of technology's kinder decisions. A semiconductor sits between these two behaviors. Silicon is the classic example. Its band gap is not so tiny that it behaves like a normal metal, but not so large that electrons are permanently locked away. With the right conditions and with carefully added impurities through a process called doping, silicon can be made to conduct electricity in controlled ways. That control is the foundation of modern electronics. This band picture grew from the development of quantum mechanics and solid-state physics. Felix Bloch played a major role by describing how electrons behave in periodic crystal structures. His work helped show that electrons in a crystal can be understood through wave-like states shaped by the repeating arrangement of atoms. Other physicists, including Arnold Sommerfeld, Leon Brillouin, Rudolf Peierls, and many more, helped build the framework that made solids understandable through quantum theory. The practical consequences were enormous. At Bell Labs in the 20th century, John Bardeen, Walter Brattain, and William Shockley developed the transistor, a tiny device that could control electrical signals. The transistor replaced many bulky vacuum tubes and became the foundation of modern computing. Every phone, laptop, satellite, camera, and digital system depends on the ability to control electrons inside solids. Beneath the smooth glass of a screen and the quiet hum of a processor is an ocean of quantum band structure doing very precise work. Light-emitting diodes also depend on quantum energy bands. In a light-emitting diode, electrons move between energy states in a semiconductor and release photons. The color of the light depends on the energy difference involved. This is why different semiconductor materials can produce red, green, blue, or other colors of light. A modern screen is not merely glowing, it is using controlled quantum transitions to create images one tiny light source at a time. Solar cells work through a related principle in reverse. Photons from sunlight enter a semiconductor and transfer energy to electrons. If the photon has enough energy to move an electron across the band gap, the solar cell can help turn that light energy into electrical energy. Not every photon is useful in the same way, because the energy of the photon must fit the material's electronic structure. Once again, the size of the quantum step matters. Lasers also rely on carefully controlled energy states. In many lasers, atoms, molecules, or semiconductor materials are arranged so that photons can stimulate the emission of more photons with matching properties. The result is coherent light, unusually organized and precise. Lasers scan barcodes, carry internet signals through optical fibers, read disks, guide surgery, measure distances, and quietly make science fiction feel slightly underdressed. The remarkable thing is that all of this depends on matter being predictable. Quantum physics is often described as strange, and it is, but it is not vague in the sense of being unusable. The quantum rules inside solids are precise enough for engineers to build entire technologies from them. Silicon chips contain billions of transistors, each relying on the controlled movement of electrons through semiconductor structures. The scale is tiny, but the reliability is extraordinary. So the quantum energy inside solids is not an exotic force hidden beyond ordinary experience. It is inside the materials that support ordinary experience. It is in the screen, the circuits, the solar panel, the camera sensor, the light bulb, the laser, and the memory chip. It is in the difference between metal and glass, between diamond and graphite, between a wire that conducts and a coating that protects. The solid world feels firm, simple, and dependable, yet its dependability comes from quantum rules. The hidden energy beneath reality is not making matter blurry or magical. It is making matter structured enough to build a world that works. The picture of the quantum world began with particles and waves, photons and electrons, atoms and energy levels. That picture was already strange enough. It showed that light could arrive in packets, electrons could behave like waves, and matter could only hold certain allowed energies. But as physicists tried to make quantum theory fit with special relativity, the story deepened again. Particles were no longer the deepest ingredients. Beneath them were fields. A field is something spread through space that can have a value at every location. The idea was not new. Michael Faraday and James Clerk Maxwell had already shown that electricity and magnetism could be described using fields. The electromagnetic field was not just a convenient drawing. It was a real physical entity, capable of carrying energy and momentum through space as light. A radio wave, a beam of sunlight, and the glow from a lamp are all disturbances in the electromagnetic field. Quantum field theory takes this idea further. It says that the basic ingredients of reality are not tiny solid beads moving through empty space, but fields that extend throughout space. What humans call particles are excitations of those fields. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Quarks are excitations of quark fields. The particles detected in experiments are real, but they are not little classical balls with crisp edges and private travel plans. They are quantum disturbances in underlying fields. This shift matters because it changes what the hidden world beneath matter looks like. In older images, an electron might be pictured as a tiny dot orbiting a nucleus, like a planet around a star. That picture is useful only as a stepping stone, and a rather wobbly one. In modern physics, an electron is not a miniature sphere quietly moving through a perfect emptiness. It is a quantum excitation associated with the electron field, carrying properties such as electric charge, mass, spin, and energy. The electron field is present everywhere. This does not mean electrons are everywhere in the ordinary sense. It means the field exists throughout space, and where it is excited in the right way, an electron can appear as a detectable particle. A helpful comparison is the surface of a pond. though every comparison eventually starts to limp when quantum theory enters the room. A ripple on the pond is not separate from the pond, it is a pattern in the pond. In a similar spirit, a particle is not separate from its field. It is a quantum pattern of excitation in that field. One of the great turning points on the road to quantum field theory came from Paul Dirac. In the late 1920s, Dirac tried to combine quantum mechanics with Einstein's special relativity. This was not optional decoration. Quantum mechanics described the small world with remarkable success, while special relativity described how space, time, energy, and motion behave when speeds approach the speed of light. A deeper theory needed to respect both. Dirac's equation for the electron was astonishing. It naturally included the property called spin, which had already appeared in quantum physics, and it also suggested something unexpected. The mathematics seemed to allow a counterpart to the electron with the same mass but opposite electric charge. This was not merely a mathematical inconvenience to be swept under a rug and politely ignored. It pointed toward antimatter. In 1932, Carl Anderson discovered the positron while studying cosmic rays. The positron is the antimatter counterpart of the electron. It has the same mass as the electron but a positive electric charge. Anderson observed its track in a cloud chamber, where charged particles leave visible trails as they pass through vapour. The discovery confirmed one of Dirac's most remarkable predictions. The universe had not only matter, but antimatter too. Antimatter is not science fiction, though science fiction has certainly enjoyed borrowing it and giving it dramatic lighting. Positrons are used in positron emission tomography, a medical imaging technique that helps map processes inside the body. Antimatter also appears naturally in certain radioactive decays and in high-energy particle interactions. Its existence shows that the quantum fields beneath matter are richer than ordinary intuition suggests. Quantum fields carry energy. They can interact with one another. They can create and absorb particles. They provide the framework for understanding forces at the smallest scales. In quantum electrodynamics, electrically charged particles interact through the electromagnetic field, with photons acting as the quanta of that field. In quantum chromodynamics, quarks interact through gluon fields, producing the strong nuclear force that binds quarks into protons and neutrons. In the electroweak theory, the electromagnetic and weak nuclear interactions are understood as related aspects of a deeper framework. This field-based view also changes the meaning of empty space. In classical thinking, empty space might seem like a blank stage where particles move around. But in quantum field theory, the fields remain even when there are no ordinary particles present. The lowest energy state of those fields is called the quantum vacuum. It is not full of little visible objects, but it is not simple nothingness either. It is the baseline state of fields that can still have physical consequences. The hidden quantum energy beneath reality is therefore better described through fields than through isolated particles. Particles are what appear when fields are excited in specific ways. Forces arise through field interactions. Light, matter, radiation, and many forms of energy exchange become part of one deeper language. This does not make the everyday world less real. It makes it more remarkable. The solidity of a table, the glow of a screen, the warmth of sunlight, the chemistry of a living cell, and the atoms in a hand all rest on fields that cannot be seen directly. Reality is not built from little hard dots moving through nothing. It is built from fields, excitations, interactions, and energy patterns so precise that they can form stars, stones, oceans, and thoughts. The deeper physics goes, the less empty the universe becomes. Beneath particles are fields, beneath stillness is structure, and beneath the ordinary surface of matter, quantum energy is not floating mysteriously through space. It is woven into the fields from which particles themselves arise. The electromagnetic field is one of the most familiar hidden things in the universe. It is hidden because no one sees the field itself in the way they see a chair, a candle, or a bright moon in a dark sky. Yet its effects are everywhere. It is involved when a magnet pulls on iron, when lightning forks through a storm cloud, when a radio signal crosses a city, when a phone screen glows, when sunlight warms skin, and when the eye receives the photons that become vision. Electricity and magnetism were once treated as separate mysteries. Electric charge could attract and repel. Magnets could tug on certain metals and line themselves with Earth's magnetic field. Sparks could leap through air, and compass needles could turn as if listening to invisible instructions. The deeper unity between electricity, magnetism and light took time to emerge, and it became one of the great achievements of 19th century physics. Michael Faraday played a central role in changing how scientists imagined physical influence. Faraday did not think of electric and magnetic effects merely as forces reaching mysteriously across empty space. He pictured lines of force filling the space around charges and magnets. His field concept gave physics a new way to understand nature. The space around an object was not just a blank emptiness waiting politely for something to happen. It could have structure, it could be active, it could store energy and guide motion. James Clerk Maxwell then transformed Faraday's physical intuition into a powerful mathematical theory. Maxwell's equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. In spoken form, the idea is wonderfully elegant. Electricity and magnetism can sustain one another as a travelling wave. Maxwell calculated that this wave should move at the speed of light, leading to the extraordinary conclusion that light itself is an electromagnetic wave. That meant visible light, infrared radiation, ultraviolet radiation, radio waves, microwaves, X-rays, and gamma rays all belong to the same family. They were not completely different substances. They were different forms of electromagnetic radiation, distinguished by wavelength, frequency, and energy. A radio wave crossing the night, a microwave warming food, and a blue photon from a distant star are all expressions of the electromagnetic field. They differ enormously in scale and energy, but they are relatives. A slightly odd family reunion, perhaps, but still a family. Classical electromagnetism was already a field theory before quantum physics arrived. It described fields spread through space, carrying energy and momentum. This prepared the ground for quantum field theory, where fields became even more fundamental. Once the electromagnetic field was treated quantum mechanically, light could be understood not only as a wave, but also as packets of field excitation. These packets are photons. A photon is the quantum excitation of the electromagnetic field. It carries energy and momentum, but it has no rest mass. It can behave like a particle in some situations and like a wave in others, though it is really a quantum object rather than a miniature bead of light. When an atom emits light, it releases a photon. When a solar panel absorbs sunlight, photons transfer energy to electrons. When a camera sensor forms an image, photons are counted and converted into electrical signals. When the retina detects light, photons trigger molecular changes that begin the process of sight. The quantum theory of light and electrically charged particles is called quantum electrodynamics. It explains how electrons, positrons, photons, and other charged particles interact through the electromagnetic field. Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson were central figures in developing and clarifying this theory in the 20th century. Their work helped turn quantum electrodynamics into one of the most precise and successful theories in all of science. Quantum electrodynamics does not simply say that charged particles push and pull each other in a vague way. It describes interactions through the exchange and behavior of photons, using the language of quantum fields. Feynman diagrams became a famous visual tool for representing these interactions, although the diagrams are not little cartoons of particles literally taking those exact paths. They are a compact way of organizing calculations. Physics, being physics, found a way to make doodles look intimidatingly useful. One of the great triumphs of quantum electrodynamics is its extraordinary precision. It has been used to predict subtle properties of the electron, including its magnetic behavior, to remarkable accuracy. The electron has a property called magnetic moment, which is affected by quantum interactions with the electromagnetic field. Measurements and predictions agree to an astonishing number of decimal places. This does not mean every mystery is solved, but it does show that the theory describes part of reality with almost unreasonable success. The electromagnetic field also shapes chemistry. Electrons are attracted to positively charged atomic nuclei. Atoms bond because charged particles interact electromagnetically under quantum rules. The stiffness of solids, the flow of electricity, the colours of pigments, the structure of molecules, and the reactions inside living cells all depend on electromagnetic interactions. Gravity may dominate planets and galaxies, but electromagnetism does much of the fine work of building the ordinary material world. It is the quiet craftsman of atoms and molecules. Starlight is electromagnetic field energy travelling across space. Some photons leave the surface of a star and journey for years. Others travel for thousands, millions, or billions of years before entering a telescope. Radio waves can carry human voices, music, spacecraft signals, and data across large distances. Lasers use the electromagnetic field in a highly organized form, producing coherent light useful in medicine, communication, industry, and research. Even a simple reflection in a mirror is an exchange between light and electrons at the surface of matter. The simple act of seeing is therefore not simple at all. Photons move from a source, or bounce from an object and enter the eye. Their energies and wavelengths carry information about colour, brightness, shape, and texture. The brain then builds a visual world from signals that began as tiny excitations of the electromagnetic field. The room seems immediate and solid, yet it is known through light that has crossed space and interacted with matter before becoming sensation. The hidden quantum energy beneath reality is deeply present in this field. It is in every photon, every chemical bond, every electric current, every radio signal, every laser pulse, and every glimmer of starlight. The electromagnetic field is not merely a background feature of the universe. It is one of the main ways reality speaks to itself, moving energy and information through space with a precision that is both ordinary and astonishing. Empty space sounds simple. It sounds like the absence of things. Remove the air, remove the dust, remove the light, remove every atom, and surely what remains should be nothing at all. A clean blank, a perfect silence. A cosmic room after everything has politely left. But quantum field theory gives empty space a more interesting meaning. In modern physics, the vacuum is not simple nothingness. It is the lowest energy state of the quantum fields that fill space. That phrase matters. The vacuum is not empty because the fields have vanished. It is empty in the sense that those fields contain no ordinary detectable particles. The stage is quiet, but the stage itself has not disappeared. This is very different from the older image of particles moving through a blank background. Quantum fields are present everywhere, and particles are excitations of those fields. When the electromagnetic field is excited in a certain way, a photon can be present. When the electron field is excited in a certain way, an electron can be present. If no ordinary particles are detected, the fields are still there in their lowest possible state. That lowest state is what physicists call the quantum vacuum. The strange part is that the lowest possible state does not usually mean zero energy. In quantum theory, a system can have 0-point energy, which is residual energy that remains even when the system is in its ground state. A simple way to feel the idea is to imagine a tiny quantum oscillator. In classical physics, it could sit perfectly still with no motion and no energy. In quantum physics, uncertainty prevents certain systems from being completely motionless in that absolute classical sense. Even the lowest state can retain a minimum amount of energy. That does not mean the vacuum is a secret battery waiting to power cities, spaceships, or a suspiciously glowing toaster. Vacuum energy is real as a concept in quantum field theory, but it is not a limitless usable power source. This point is important because the phrase quantum energy is often dragged into claims that sound scientific, but quietly walk away from actual physics. Energy conservation still applies. Thermodynamics still applies. A system's lowest energy state is not a convenient fuel tank. If something is already at its lowest accessible state, extracting useful work from it is not as simple as opening a tap. The quantum vacuum is subtle. It is not magical. It does not give out free energy because someone used the word quantum with enough confidence. In real physics, claims must survive experiments, equations, and the very unforgiving habit of nature not caring how exciting an idea sounds. One idea often connected with the quantum vacuum is vacuum fluctuations. These are usually described in popular science as particles popping in and out of existence. That image can be helpful for a first impression, but it can also mislead. It may make the vacuum sound like a tiny fireworks display, with miniature particles appearing, waving and vanishing before anyone can ask for identification. In a more careful sense, vacuum fluctuations are temporary variations in the activity of quantum fields. They arise from the mathematical structure of quantum field theory and from the uncertainty built into quantum systems. These fluctuations are not ordinary particles in the same sense as a photon detected by a camera or an electron measured in a laboratory. They are not little beads briefly cheating reality. They are features of fields and calculations that help describe how quantum systems behave. The vacuum can influence measurable effects, but it should not be pictured too literally as a busy crowd of tiny objects constantly materializing from true nothing. The truth is stranger, and also more disciplined. One of the most famous phenomena associated with vacuum behavior is the Casimir effect. Hendrik Casimir, working with Dirk Polder in the 1940s, studied how quantum fields might behave between objects placed extremely close together. The basic Casimir effect is often described using two uncharged conducting plates separated by a very tiny distance. Because of the boundary conditions created by the plates, the allowed modes of the electromagnetic field between them differ from those outside them. The result is a small attractive force between the plates. This force is extremely tiny in ordinary circumstances, becoming noticeable only at very small separations, but it is real enough to measure. Later precision experiments confirm the effect with increasing care, turning what sounds like an abstract quantum idea into something detectable in the laboratory. It does not mean plates are being pushed together by mystical emptiness. It means that the quantum vacuum, when shaped by boundaries, can produce measurable consequences. The Casimir effect is a beautiful example because it is quiet. It does not involve a star exploding, a particle accelerator roaring, or a dramatic cosmic event. It involves empty space, metal surfaces, and a tiny force that only appears clearly when the conditions are controlled with great precision. It is the kind of effect that whispers rather than shouts. But in science, a whisper can still rewrite the room. Vacuum energy also connects to much deeper puzzles. In cosmology, the energy associated with empty space is often discussed in relation to the cosmological constant and dark energy, the name given to whatever is driving the accelerated expansion of the universe. But there is a profound problem. Simple estimates from quantum field theory and the observed value connected with cosmic acceleration do not naturally agree. The mismatch is not small. It is one of the most serious unresolved tensions in modern physics. So empty space is not empty in the old intuitive sense. It is the quiet ground state of fields that extend throughout the universe. It can have zero-point energy. It can show measurable effects such as the Casimir effect. It can influence some of the deepest questions about cosmology. But it is not a mystical reservoir, and it is not an excuse to abandon careful science. The hidden quantum energy beneath reality is perhaps nowhere more subtle than in the vacuum. It is present not as a glowing substance, but as the baseline structure of fields themselves. Even when particles are absent, the fields remain. Even when space looks empty, physics has not gone silent. The Lamb shift is one of those scientific discoveries that does not look dramatic from the outside. It does not involve a galaxy tearing itself apart, or a particle accelerator smashing matter at nearly the speed of light, or a telescope staring into the edge of the observable universe. It involves hydrogen, the simplest atom, and an incredibly tiny difference in energy. Yet that tiny difference became one of the clearest signs that the quantum vacuum is not just a philosophical curiosity. It has measurable consequences. Hydrogen is often treated as the cleanest atom in physics. It has one proton and one electron, which makes it the simplest natural laboratory for testing ideas about atomic structure. Niels Bohr's early model had already shown that hydrogen's spectral lines could be explained by electrons occupying discrete energy levels. Later, Erwin Schrödinger's wave mechanics gave a deeper and more accurate description, replacing simple circular orbits with quantum states described by wave functions. By the middle of the 20th century, hydrogen had become a kind of quiet, proving ground for quantum theory. According to the simpler version of quantum mechanics, certain energy states in hydrogen should have exactly the same energy. They were different in their detailed quantum properties, but the basic theory predicted a perfect match. This was not a rough guess. It followed from the mathematical structure of the theory. If the prediction were right, transitions involving those states should behave in a particular way. But nature had placed a tiny correction in the margins. In 1947, Willis Lamb and Robert Rutherford carried out a careful experiment that measured a small difference between two energy levels of hydrogen that were expected to be identical. This difference became known as the Lamb shift. It was not large. It was not something that would show up in ordinary life. No one could look at hydrogen gas and casually notice that one of its energy levels had been nudged slightly, unless they were having a truly unusual afternoon. But with precise equipment, the shift could be measured. The historical timing mattered. After the Second World War, physicists had access to improved microwave technology, partly developed through wartime radar research. These tools allowed them to probe atoms with much greater precision. Lamb and Rutherford used microwave techniques to examine the fine structure of hydrogen, revealing that the atom was not quite behaving according to the simpler theory. Something deeper was affecting the electron's energy. That deeper explanation came from quantum electrodynamics, the quantum theory of light, electrons, and their interactions with the electromagnetic field. In quantum electrodynamics, an electron in an atom does not sit in isolation from everything else. It interacts with the electromagnetic field, including the field in its vacuum state. The vacuum is not full of ordinary light or detectable particles, but it is still the lowest energy state of a real quantum field. Its presence can subtly affect measurable systems. The Lamb shift helped show that the energy levels of hydrogen are influenced by interactions between the electron and the electromagnetic vacuum. One way of describing this is that the electron is affected by fluctuations in the quantum electromagnetic field. Another part of the explanation involves the electron interacting with its own electromagnetic field in a way that must be handled carefully by quantum electrodynamics. The technical details are mathematically demanding, but the central point can be said calmly. The supposedly empty vacuum slightly changes the allowed energy levels of an atom. This is extraordinary. The hydrogen atom is not a loose guess. It is one of the most precisely studied systems in physics. If its energy levels are shifted by a tiny amount, that shift must be explained. Quantum electrodynamics explained it with remarkable success. The Lamb shift became one of the early triumphs that helped establish the theory as a powerful and accurate description of the electromagnetic interaction. It also showed why the earlier picture of atomic energy levels needed to become richer. Bohr's model gave the first useful staircase. Schrödinger's wave mechanics refined the staircase into a deeper set of quantum states. But quantum field theory showed that the staircase itself is subtly shaped by interactions with fields, even when those fields are in their vacuum state. The atom is not sealed away from the rest of reality. Its energy levels are part of a wider quantum field environment. The Lamb shift is tiny, but tiny does not mean imaginary. Many of the most important discoveries in physics come from small mismatches between prediction and measurement. A tiny irregularity in the orbit of Mercury helped point toward general relativity. Small spectral details reveal the composition of distant stars. Minute differences in particle behavior test the standard model. Physics often advances not because nature shouts, but because it whispers with suspicious precision. The Lamb shift also helps correct a common misunderstanding about hidden quantum energy. The vacuum does not need to glow. It does not need to shake tables, hum audibly, or power a kettle from the emptiness between its atoms. Its effects can be far more subtle than that. They can appear as a slight adjustment in the measured energy of an atomic state. They can be found only by careful experiments, patient mathematics, and instruments sensitive enough to notice what ordinary senses never could. This makes the Lamb shift a beautiful example of scientific humility. Human intuition might say that empty space should do nothing. Classical thinking might imagine an atom as a little system sitting inside a blank container. But quantum field theory says that the container is not blank. Fields remain. Their lowest energy states matter, and under the right conditions, their influence can be measured. Willis Lamb received the Nobel Prize in Physics in the 1950s for work connected with these discoveries. The Lamb shift became part of the evidence that quantum electrodynamics was not merely clever mathematics, but a theory capable of describing real atomic behavior with extraordinary accuracy. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson would help shape quantum electrodynamics into the precise framework that explained such effects. The subtle energy of the vacuum is not something that floats visibly in space. It is not an extra substance added to the universe. It is part of the behavior of quantum fields themselves. In the Lamb shift, that behavior leaves a delicate fingerprint on hydrogen, the simplest atom of all. The hidden quantum energy beneath reality is sometimes grand, as in stars and nuclear reactions, but sometimes it is almost impossibly quiet, a tiny shift in an atom's energy, revealing that even the vacuum has a say in the architecture of matter. Mass feels like one of the most basic facts about reality. A stone has mass, a body has mass, a planet has mass, even a cup of tea has mass, though its emotional importance may exceed what any scale can measure. Mass is what gives objects inertia, meaning resistance to changes in motion. It is also what allows matter to take part in gravity. It seems solid, obvious, and almost too familiar to question. But modern physics shows that mass is not a simple ingredient sprinkled evenly into particles at the beginning of time. Some of it comes from interactions, some of it comes from energy. And part of the story leads to one of the most famous invisible structures in modern science, the Higgs field. The Higgs field is a quantum field that exists throughout space. Unlike many other fields, it has a non-zero value even in its lowest energy state. That means the Higgs field does not vanish in empty space. It is present everywhere, quietly forming part of the background structure of the universe. This makes it especially relevant to the idea of hidden quantum energy beneath reality. Even when space seems empty, one of the field-shaping particle properties is still there. The basic idea of the Higgs mechanism is that certain elementary particles gain mass through their interaction with the Higgs field. The more strongly a particle interacts with the Higgs field, the more mass it has. The less strongly it interacts, the less mass it has. Photons, for example, do not gain mass from the Higgs field, which is why light can travel through empty space at the speed of light. Electrons do interact with the Higgs field, giving them a small but crucial mass. Without that mass, atoms, chemistry, and ordinary matter would be radically different. A common comparison imagines a particle moving through a kind of invisible medium, slowed or affected by its interaction with that medium. That image can be helpful as a first step. but it should not be taken too literally. The Higgs field is not a sticky syrup filling space. Particles are not physically dragging themselves through cosmic treacle, although the universe has certainly tried stranger things. The real explanation belongs to quantum field theory and symmetry breaking. The Higgs field changes the behaviour of certain fields in a way that gives their particles mass while preserving the deeper mathematical consistency of the Standard Model. The development of the Higgs mechanism involved several physicists working in the 1960s. Peter Higgs is the name most commonly attached to it, but the broader idea was also developed by François Englert and Robert Brute, as well as Gerald Guralnick, Carl Hagen and Tom Kibble. Their work showed how particles could acquire mass through a field without breaking the structure of the theory. This was essential for explaining the weak nuclear force, which is carried by massive particles while keeping the theory mathematically coherent. The weak nuclear force is involved in processes such as radioactive beta decay and nuclear fusion in stars. The particles that carry the weak interaction, called W and Z bosons, are much heavier than the photon, even though the weak force and the electromagnetic force are related in electroweak theory. The Higgs mechanism helps explain why these force-carrying particles have mass, while the photon remains massless. It is one of the reasons the Standard Model fits together at all. For many years, the Higgs field was strongly supported by theory, but the particle associated with it had not yet been directly observed. In quantum field theory, fields can have excitations. The Higgs boson is the quantum excitation of the Higgs field. Finding it required enormous energies, extraordinary detectors, and the combined work of thousands of scientists and engineers. In 2012, CERN announced the discovery of a new particle consistent with the Higgs boson at the Large Hadron Collider, the enormous particle accelerator near Geneva. The discovery came from the ATLAS and CMS collaborations, two major experiments designed to study high-energy particle collisions. Protons were accelerated around a circular tunnel and smashed together, briefly creating conditions where heavy, short-lived particles could appear. The Higgs boson itself decays almost immediately, so scientists identified it by studying the particles produced from its decay patterns. The discovery was a major confirmation of the Standard Model. It did not mean physics was finished, which is fortunate because physicists would otherwise have had to take up gardening with suspicious intensity. The Higgs boson confirmed that the Higgs field was not merely a clever theoretical device. It pointed toward a real field with measurable consequences. Still, the Higgs field does not explain all mass. This is a very important point. It gives mass to certain elementary particles such as electrons and quarks, but most of the mass in ordinary matter does not come directly from the Higgs field. Protons and neutrons are made of quarks, but the quarks themselves account for only a small part of their total mass. Most of the mass of protons and neutrons comes from the energy of the strong nuclear force, especially the energy of gluons and the intense motion and interactions of quarks inside them. This is a beautiful and slightly unsettling idea. The mass of ordinary objects mostly comes from energy trapped in the strong force binding quarks and gluons inside atomic nuclei. A stone feels heavy not simply because its particles carry little built-in masses, but because energy itself contributes to mass. Einstein's relation between mass and energy sits quietly in the background here, often spoken as energy equals mass multiplied by the speed of light multiplied by the speed of light. The Higgs field, then, is not the whole answer to mass, but it is a vital part of the answer. It explains why certain fundamental particles have rest mass at all. It helps make electrons massive enough to form atoms. It helps shape the weak nuclear force. It shows that properties which seem built into particles may arise from their relationship with invisible fields. Mass may feel like the most solid thing in the world, but even mass has hidden depth. Part of it comes from the Higgs field. Much of it comes from binding energy inside protons and neutrons. Beneath the familiar weight of matter lies a field-filled reality where energy, interaction, and structure create what feels solid to the hand. The hidden quantum energy beneath reality is not only behind light, atoms, and empty space, it is also part of why matter has weight at all. Inside every atom, beneath the cloud of electrons and beneath the chemistry those electrons allow, there is a much denser centre. The atomic nucleus is tiny compared with the atom as a whole, but it contains almost all of the atom's mass. If an atom were expanded to the size of a cathedral, the nucleus would still be a small object near the middle, while the electrons would occupy the vast surrounding space. Matter feels solid not because atoms are packed full like little marbles, but because quantum fields, electric forces, electron states, and nuclear structure work together in precise and deeply layered ways. The nucleus is made of protons and neutrons, which are often called nucleons when discussed together. Protons carry positive electric charge. Neutrons have no electric charge. That creates an immediate puzzle. If protons all have positive charge, they repel one another through the electromagnetic force. Place several protons close together, and they should push apart fiercely. Yet atomic nuclei can hold many protons together in a space unimaginably smaller than the atom. Something stronger must be acting at very short distances. That something is connected to the strong nuclear force. At the deepest level, the strong interaction binds quarks together inside protons and neutrons, using particles called gluons. Protons and neutrons are not elementary little beads. They are made from quarks, constantly interacting through gluon fields, with enormous energy contained in the motion and binding of that system. Most of the mass of protons and neutrons comes not from the bare masses of the quarks themselves, but from the energy of this strong interaction. There is also a residual strong nuclear force that acts between protons and neutrons inside the nucleus. This residual force helps hold the nucleus together, despite the electric repulsion between protons. It works only across extremely tiny distances, roughly the scale of the nucleus. At larger distances it fades quickly. This is why nuclei can be stable, but only in particular arrangements. The balance between the strong force, electromagnetic repulsion, quantum states, and the number of protons and neutrons determines whether a nucleus can last for billions of years or decay almost instantly. Nuclear energy comes from changes in nuclear binding energy. Binding energy is the energy associated with holding a nucleus together. A tightly bound nucleus is more stable than a loosely bound one. If a nuclear process moves matter toward a more stable arrangement, energy can be released. The energy does not appear from nowhere. It comes from the difference between the energy of the starting arrangement and the energy of the final arrangement. In nuclear reactions, a small amount of mass can correspond to a large amount of energy, expressed by Einstein's famous relation. Energy equals mass multiplied by the speed of light multiplied by the speed of light. This is why nuclear processes are so powerful. The speed of light is enormous, and multiplying by it twice makes even a small amount of mass equivalent to a very large amount of energy. The equation is not a magic spell, although it has certainly been treated with the correct amount of awe. It is a statement that mass and energy are deeply connected, and nuclear physics is one of the places where that connection becomes impossible to ignore. Nuclear fission and nuclear fusion release energy in different ways. In fission, a heavy atomic nucleus splits into smaller nuclei. Some heavy nuclei, such as uranium or plutonium isotopes, can become more stable by breaking apart into medium-sized fragments, releasing energy and often additional neutrons. This process became understood through the work of scientists including Otto Hahn, Fritz Strassmann, Lise Meitner, and Otto Frisch in the late 1930s. Meitner and Frisch helped interpret the splitting of the nucleus as fission, drawing on the physics of nuclear binding energy. Fusion works in the opposite direction. In fusion, light nuclei combine to form heavier nuclei. The simplest and most important example in the cosmos is hydrogen fusion in stars. When light nuclei fuse into more tightly bound arrangements, energy is released. Hans Bethe helped explain the nuclear processes powering stars, including the proton-proton chain that dominates in stars like the Sun, and the carbon-nitrogen-oxygen cycle that becomes more important in hotter, more massive stars. The Sun is the gentlest-looking nuclear reactor imaginable from Earth, mostly because it is safely about 150 million kilometers away and politely filtered by space. In its core, hydrogen nuclei are transformed through a chain of reactions that ultimately produces helium, along with energy carried outward as radiation and particles. This energy takes a long and complicated journey through the solar interior before escaping as sunlight. The warmth on skin, the glow on leaves, the weather in the atmosphere, and almost all food on Earth trace back to nuclear fusion in the Sun. But fusion in the Sun has its own quantum secret. Protons repel one another because they are positively charged. Even in the hot, dense solar core, they usually do not have enough classical energy to overcome this electric repulsion directly. Quantum tunneling allows a small fraction of them to pass through the energy barrier and get close enough for the strong nuclear force to bind them. Without quantum tunneling, the Sun's fusion rate would be far too low to shine as it does. Sunlight is therefore not just nuclear energy, it is nuclear energy made possible by quantum behavior. Ernest Rutherford helped reveal the nuclear structure of the atom in the early 20th century through scattering experiments that showed atoms contain a tiny, dense nucleus. Enrico Fermi made major contributions to nuclear physics, including work on neutron interactions and beta decay. The development of nuclear science became one of the most consequential and morally complex stories in modern history, leading to power generation, medicine, weapons, astrophysics, and a deeper understanding of matter itself. Nuclear energy is not separate from quantum physics. It depends on quantist nuclear states, particle interactions, binding energy, the strong force, the weak force, tunneling, and the relation between mass and energy. The nucleus may seem like a tiny central knot inside the atom, but within it are forces and energy scales far beyond ordinary chemistry. The hidden quantum energy beneath reality is therefore not only in photons, atoms, chemical bonds, solids, fields, and the vacuum. It is also in the nucleus, where protons and neutrons are held together by forces so strong and subtle that tiny changes in binding can light stars, transform elements, and release energies that shaped both the cosmos and human history. Quantum tunneling is one of those ideas that sounds as if physics has quietly lost patience with common sense. In the everyday world, if an object does not have enough energy to cross a barrier, it does not cross. A ball rolling toward a hill will climb partway up, slow down, and roll back if it lacks enough energy to reach the top. It does not simply appear on the other side of the hill after deciding that the usual route looked tiring. Classical physics is very clear about this. A barrier is a barrier. If a particle has less energy than it needs to overcome that barrier, it should be reflected or trapped. This works beautifully for ordinary objects. A car without enough speed will not coast over a steep hill. A marble in a bowl will not escape unless it gains enough energy to climb the side. A tired person under a blanket will not suddenly tunnel to the kitchen, no matter how strongly the biscuits cool. But quantum systems are not described as tiny classical objects following definite paths. They are described by wave functions, and wave functions can extend into regions that would be forbidden in classical physics. When a quantum particle encounters an energy barrier, its wave function does not always stop abruptly at the edge. It can leak into the barrier and sometimes extend beyond it. If there is a non-zero probability of finding the particle on the far side, then the particle may be detected there. That is quantum tunneling. This does not mean the particle secretly digs a little passage, or borrows energy, or finds a hidden door marked for quantum use only. Those images can be fun, but they are misleading if taken too literally. Tunneling is not a particle cheating the rules. It is the particle obeying quantum rules instead of classical ones. The wave function gives a probability distribution, and under certain conditions that probability reaches beyond a barrier that classical physics would treat as impossible. The chance of tunneling depends on several things. A thinner barrier is easier to tunnel through than a thicker one. A lower barrier is easier than a higher one. A lighter particle is usually more likely to tunnel than a heavier one. This is one reason tunneling is important for electrons, protons, and other small particles, but not for footballs, cars, or household furniture. Technically, the quantum description still applies to larger objects, but the tunneling probabilities become so fantastically tiny that they are effectively zero. A sofa will not tunnel through the wall. It will remain in the room, looking smugly classical. One of the first major successes of tunneling came from the study of alpha decay. In alpha decay, an unstable atomic nucleus emits an alpha particle, which is made of 2 protons and 2 neutrons. The puzzle was that the alpha particle seemed to escape from the nucleus, even though, classically, it did not appear to have enough energy to climb over the barrier created by the nuclear forces and electric repulsion. In the late 1920s, George Gamow explained alpha decay using quantum tunneling. The alpha particle did not need to go over the barrier in the classical sense. Its wave function allowed a probability of appearing outside the nucleus. This was a powerful moment because it showed that tunneling was not merely an abstract mathematical oddity. It explained a real nuclear process. It also helped connect quantum mechanics to radioactivity, nuclear stability, and the deep energy structure of matter. A tiny probability, repeated across enormous numbers of atoms, could become a measurable half-life. Some nuclei decay quickly, others last for thousands, millions, or billions of years. Tunneling helps explain why escape from the nucleus can be rare, but not impossible. Tunneling is also essential inside stars. In the Sun's core, hydrogen nuclei, which are protons, move at high speeds because the temperature is extremely high, but protons carry positive electric charge, so they repel one another. Classically, many of them would not have enough energy to overcome this electric repulsion and get close enough for the strong nuclear force to bind them. Quantum tunneling allows a small fraction of protons to pass through the barrier. That small fraction is enough to sustain nuclear fusion over billions of years. This means sunlight depends on tunneling. The warm light falling across Earth, the energy driving weather, the growth of plants, the food chain, and almost every familiar form of life are connected to quantum particles doing something classical physics would not permit. The sun shines, not because every proton easily smashes through the barrier, but because the quantum probability is small yet persistent. Nature does not always need a large chance. Sometimes it only needs a tiny chance tried often enough. Tunneling is not only found in stars and unstable nuclei, it has practical uses in technology. A scanning tunneling microscope uses tunneling to study surfaces at atomic scales. A sharp conducting tip is brought extremely close to a surface, close enough that electrons can tunnel between the tip and the material. By measuring the tunneling current, scientists can map surfaces with astonishing precision, even resolving individual atoms under the right conditions. The instrument helped open a new view of the nanoscopic world, where surfaces are not smooth planes but landscapes of atoms. Tunnel diodes also use quantum tunneling. These electronic devices allow current to flow through a barrier in a way that depends on quantum behavior, producing unusual electrical properties useful in certain high-speed circuits. Tunneling also matters in flash memory, some semiconductor devices, nuclear physics, chemistry, and even certain biological discussions where proton or electron tunneling may play roles in specific reactions. It is not a rare party trick of the quantum world. It is one of its working habits. The deeper lesson is that energy barriers are not always absolute walls. In classical physics, if the energy is too low, the answer is simply no. In quantum physics, the answer can become probably not, but not impossible. That distinction is subtle, but it changes the universe. It allows alpha particles to escape nuclei. It helps stars shine. It allows microscopes to feel the shapes of atoms without touching them in the ordinary sense. The hidden quantum energy beneath reality is not always about huge explosions, blazing stars, or enormous amounts of power. Sometimes it is about probability. Sometimes it is about the wave-like nature of matter creating possibilities where classical physics allows none. A barrier remains a barrier, but at the quantum scale, reality does not always treat barriers as the final word. Tunneling shows that the deep world is not built only from forces and energies, but from allowed chances. Beneath the steady surface of matter, small probabilities quietly decide what can happen, and from those quiet probabilities come radioactive decay, stellar fusion, atomic scale imaging, and the gentle fact that sunlight reaches Earth at all. To understand quantum energy fully, it is not enough to look inside atoms, solids, stars, or nuclei. The same ideas also reach back toward the earliest moments of the universe, when matter had not yet settled into the familiar form seen today. Before planets, before stars, before atoms, before even stable protons and neutrons in the ordinary sense, the universe was an extremely hot, dense, rapidly changing state, where energy and quantum fields shaped the ingredients of everything that would later exist. The Big Bang model is often pictured as an explosion, but that image can be misleading. It was not a blast of matter flying outward into empty space, like sparks from a firework spreading into a dark room. The better description is the expansion of space itself from an earlier hotter and denser condition. Space was not sitting there beforehand as a stage waiting for the universe to appear. According to the standard cosmological model, the universe was once much hotter, much denser, and far more uniform, and as space expanded, the contents of the universe cooled. This cooling is crucial. Temperature is a measure connected to the average energy of particles and radiation. In the early universe, temperatures were so high that matter could not yet exist in the calm forms familiar today. At very high energies, quantum fields interacted constantly. Particles and antiparticles could be created and destroyed. Radiation, matter and fields were locked in a restless exchange. The universe was not a collection of stars and galaxies. It was closer to an intensely hot quantum field environment where energy itself could become particles if the conditions allowed. The relationship between mass and energy is central here. Einstein's famous idea can be spoken as energy equals mass multiplied by the speed of light multiplied by the speed of light. In the early universe, energy was concentrated enough that particle creation was natural. Energy in fields could produce matter and antimatter pairs. Particles could meet their antiparticles and annihilate back into radiation. This was not magic, and not a violation of conservation. It was the deep flexibility of mass and energy under the rules of relativity and quantum field theory. As the universe expanded and cooled, this balance changed. Some particles could no longer be produced easily because the surrounding energy had dropped too low. Certain interactions froze out, meaning they became too rare to maintain equilibrium. Quarks eventually became confined inside protons and neutrons through the strong interaction. Light atomic nuclei formed during Big Bang nucleosynthesis, when protons and neutrons combined to create mostly hydrogen, helium, and traces of other light elements. Much later, after hundreds of thousands of years, the universe cooled enough for electrons to join with nuclei and form neutral atoms. That moment released one of the most important signals in cosmology, the cosmic microwave background. Before neutral atoms formed, the universe was filled with free electrons that scattered photons constantly, making space opaque. Once electrons combined with nuclei, photons could travel freely. That ancient light has been stretched by the expansion of the universe into microwave radiation, filling the cosmos as a faint afterglow. Arno Penzias and Robert Wilson detected this radiation in the 1960s, providing powerful evidence for the Big Bang model. Decades later, the Planck Space Observatory mapped the cosmic microwave background with exquisite precision, revealing tiny temperature variations across the sky. Those variations are small, but they matter enormously. The cosmic microwave background is not perfectly smooth. Its tiny differences show where the early universe was slightly denser or slightly less dense. Over cosmic time, gravity amplified those small differences. Denser regions attracted more matter, eventually helping form galaxies, clusters of galaxies, and the vast web-like structure of the universe. The night sky may look scattered and spacious, but its largest patterns trace back to delicate early irregularities. One of the most intriguing ideas in modern cosmology is cosmic inflation. Inflation proposes that, extremely early in cosmic history, the universe underwent a very brief period of extraordinarily rapid expansion. The idea is strongly associated with Alan Guth, Andrei Linde and other researchers who developed different versions of inflationary theory. Inflation helps explain why the observable universe appears so uniform on large scales, why space appears close to flat, and why tiny early fluctuations could be stretched across enormous distances. But inflation must be described carefully. It is a leading idea, and it fits many features of modern cosmology, but its detailed mechanism remains actively studied and debated. Scientists do not yet have a final confirmed description of the field or process that drove inflation. It is a powerful framework, not a completely closed chapter. This is one of those places where real science is more interesting when it is honest. The known evidence points strongly in certain directions, but the deepest explanation is still being refined. The connection to quantum energy is subtle and profound. In many inflationary models, tiny quantum fluctuations in fields during the early universe were stretched by rapid expansion until they became cosmic scale variations. These fluctuations were originally incredibly small, belonging to the quantum behavior of fields, yet after being enlarged by cosmic expansion, they may have become the seeds of galaxies. In that picture, the largest structures in the universe grew partly from the smallest possible uncertainties. There is something quietly astonishing about that. The Milky Way, galaxy clusters, dark cosmic voids, and the broad architecture of the observable universe may owe their beginnings to tiny variations in quantum fields. Not because the universe was chaotic in a careless way, but because quantum fields have fluctuations, and gravity can turn small differences into large structures over immense spans of time. The early universe reminds us that quantum energy is not only a microscopic subject, it belongs to atoms and particles, but also to cosmology. It shaped the conditions from which matter emerged. It governed particle creation and annihilation. It helped determine how fields behaved when the universe was young, hot, and dense. It may even have planted the first slight unevenness from which galaxies later formed. The hidden quantum energy beneath reality is therefore not only beneath matter in the sense of being small, it is beneath reality in the historical sense too. It lies close to the origin of structure, light, atoms, stars, galaxies, and the cosmic background still glowing faintly across the universe. The same quantum principles that make electrons occupy allowed states and photons carry packets of energy also reach back into the first chapters of cosmic history, where the universe itself was young enough for energy, fields, matter and space to be almost inseparably entwined. The universe is not only expanding, it appears to be expanding faster as time goes on. That is one of the strangest discoveries in modern cosmology, because gravity should intuitively slow cosmic expansion down. Matter attracts matter. Galaxies, clusters, gas, stars, planets, dust, and dark matter all contribute gravity. If the universe began expanding long ago, it would seem natural to expect that expansion to gradually decelerate, like a ball thrown upwards slowing under Earth's pull. But the universe, as far as observations can tell, did not follow that simple expectation. On very large scales, the expansion of space is accelerating. The name given to whatever is driving this acceleration is dark energy. It is not called dark because it is sinister, moody, or refusing to turn on a lamp. It is called dark because its nature is not directly known. Scientists can infer its presence from the behaviour of the universe, but they do not yet know exactly what it is. Dark energy is not the same thing as ordinary quantum energy. It is not a photon, not an electron's energy level, not nuclear binding energy, and not the useful energy in a battery. It should not be mixed carelessly with every other strange-sounding energy in physics, because that is how clear science slowly turns into a fog machine. But dark energy is often discussed alongside vacuum energy, because both involve a deep question: can space itself have energy? That question is not as simple as it sounds. In everyday thinking, space feels like emptiness. Objects sit in space, move through space, and are separated by space. But general relativity changed that view by showing that space and time are part of a dynamic structure. Matter and energy shape space-time, and space-time guides the motion of matter and energy. Quantum field theory added another layer by describing fields that exist throughout space, even in their lowest energy states. So when modern physics asks whether space itself has energy, it is asking something serious, not merely poetic. The evidence for accelerated expansion came sharply into view in 1998. Two research groups, the Supernova Cosmology Project and the Higgs Supernova Search Team, studied distant Type 1 supernova. These supernovae are useful because they have predictable brightness properties, making them powerful tools for measuring cosmic distances. By comparing how bright they appeared with how far away they were, astronomers could trace how the expansion of the universe had changed over time. The result was startling. The distant supernovae appeared dimmer than expected in a universe whose expansion was slowing down. The best interpretation was that the expansion of the universe had begun accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees were key figures connected with this discovery, and their work helped transform cosmology. The universe was not merely coasting outward. Something was causing the expansion of space to speed up over cosmic time. One possible explanation is the cosmological constant. Albert Einstein originally introduced the cosmological constant into his equations of general relativity in the early 20th century, at a time when many scientists thought the universe was static. The term could act as a kind of outward effect, balancing gravity and allowing a static universe in the mathematics. After Edwin Hubble's observations showed that the universe is expanding, Einstein reportedly became dissatisfied with the idea, although the famous quote about his greatest blunder has a complicated history. In modern cosmology, the cosmological constant has returned with a new meaning. It can be interpreted as a constant energy density of space itself. As space expands, the amount of matter in a given volume becomes more diluted, but a cosmological constant would remain associated with space. Its density would not thin out in the same way matter does. Over time, as matter becomes more spread out, this constant energy of space can dominate the cosmic expansion and drive acceleration. This is elegant, but it is also deeply puzzling. The cosmological constant fits many observations very well, including measurements of the cosmic microwave background, galaxy clustering, and supernova distances. The standard model of cosmology, often called lambda cold dark matter, includes a cosmological constant-like dark energy component, along with cold dark matter and ordinary matter. It is currently the simplest successful description of the large-scale universe, yet the deeper explanation remains uncertain. If dark energy is vacuum energy, then quantum field theory seems to create a serious problem. Simple estimates of vacuum energy from quantum fields are wildly different from the tiny value implied by cosmic acceleration. The mismatch is enormous. It is often called the cosmological constant problem, and it is one of the greatest unresolved problems in theoretical physics. This problem is not a small rounding error. It is not the kind of mismatch where physics can quietly blame the calculator and move on. It suggests that something very deep is not yet understood about vacuum energy, gravity, quantum fields, or the way energy associated with space should be counted. Quantum field theory works extraordinarily well for particles and forces, general relativity works extraordinarily well for gravity and cosmology. But when the two are brought together in the question of empty space and cosmic acceleration, the answer does not fall neatly into place. There are other possibilities. Dark energy might not be a true constant. It might come from a dynamic field that changes over time, sometimes called quintessence in theoretical models. It might point toward a modification of gravity on the larger scales, or it might still be best described by a cosmological constant, with the deeper quantum explanation waiting beyond current theory. Observations so far are broadly consistent with dark energy behaving very much like a cosmological constant, but the final meaning remains open. The strange thing about dark energy is its scale. Quantum energy began this journey in tiny packets of light, atomic levels, fields, particles, and vacuum effects measured with delicate instruments. Now the question has expanded to the fate of the entire cosmos. If dark energy continues behaving like a cosmological constant, distant galaxies beyond our local gravitational neighbourhood will move farther away faster and faster. Over immense timescales, the observable universe could become increasingly empty, with more galaxies slipping beyond reachable horizons. So the deepest hidden energy beneath reality may not only shape atoms, photons, chemistry, solids, nuclear reactions, and the vacuum, it may also shape the future of space itself. The same broad question keeps returning in different forms. What does energy mean when reality is examined at its deepest level? In the atom, it creates allowed states. In fields, it creates particles and interactions. In the vacuum, it refuses to become simple nothing. And in cosmology, it may be guiding the expansion of the universe toward a future more silent and more spacious than the present sky can easily suggest. For all its extraordinary success, modern physics is not finished. It has reached astonishing depths, from photons and atoms to quantum fields, nuclear binding, vacuum effects, and the accelerating universe. It can explain why light arrives in packets, why atoms have structure, why chemistry works, why stars shine, and why the electromagnetic force can be calculated with almost unreasonable precision. Yet the deeper the picture becomes, the more clearly certain blank spaces appear. That is not a weakness. It is one of the honest strengths of science. A good theory does not have to answer every possible question to be powerful. It has to explain what it claims to explain, make testable predictions, survive measurement, and show where its own boundaries may lie. Quantum physics and the standard model of particle physics have done this spectacularly well. But they have not closed every door. The standard model describes the known elementary particles and three of the four fundamental interactions: the electromagnetic force, the weak nuclear force, and the strong nuclear force. It includes quarks, leptons, gauge bosons, and the Higgs boson. It explains an enormous range of experimental results, from particle collisions to radioactive decay to the behaviour of fields at high energies. The discovery of the Higgs boson at CERN's Large Hadron Collider in 2012 was a major confirmation that the framework was pointing in the right direction. But the standard model is incomplete. It does not include gravity as a quantum force. It does not explain dark matter, the unseen mass inferred from galaxy rotation, gravitational lensing, galaxy clusters, and the large-scale structure of the universe. It does not explain dark energy, the unknown cause of cosmic acceleration. It does not fully explain why the universe contains so much matter compared with antimatter. It includes particle masses and interaction strength that are measured from nature rather than derived from a deeper known principle. It is a masterpiece, but not the final architecture. Gravity is the largest missing piece. Albert Einstein's general relativity describes gravity not as an ordinary force, but as the curvature of space-time caused by matter and energy. In this theory, planets orbit because they follow paths through curved space-time. Light bends near massive objects. time runs differently in stronger gravitational fields. Black holes, gravitational waves, and the expansion of the universe all belong to this framework. General relativity has passed test after test, from Mercury's orbit to gravitational wave detections by observatories such as LIGO and Virgo. Quantum field theory, however, describes particles and forces on the smallest scales using fields, probabilities, and quantized interactions. It works beautifully for the electromagnetic weak and strong interactions. But combining quantum field theory with general relativity has proved extremely difficult. Gravity is tied to the structure of space-time itself, while quantum theory normally assumes a background in which fields exist and evolve. When space-time becomes quantum, it is not obvious what the background even means. It is a little like trying to describe the ripples on a pond while the pond itself is no longer certain it wants to be a pond. This difficulty becomes especially sharp in extreme places, the centre of black holes, the earliest moments of the universe, and scales where gravity and quantum effect should both matter. At those depths, current theories begin to strain. General relativity predicts singularities, places where the mathematics points toward infinite density or curvature, but infinities often signal that a theory is being pushed beyond its proper domain. Quantum gravity is the search for a deeper framework that can describe gravity according to quantum principles. Several approaches exist, but none has yet been confirmed as the final answer. String theory proposes that the basic ingredients of reality may be tiny, vibrating strings rather than point-like particles, with different vibrational patterns corresponding to different particles. It offers a possible route toward including gravity, but it has not yet produced direct experimental confirmation. Loop quantum gravity takes a different approach, attempting to quantize space-time itself, suggesting that space may have a discrete structure at the deepest scale. Effective field theory treats gravity as a quantum field theory that works at lower energies, even if it is not the ultimate high-energy theory. Each approach offers insights. None has yet solved the full problem in a way that nature has clearly confirmed. The measurement problem is another unresolved question. Quantum mechanics provides extremely accurate predictions for measurement outcomes, but exactly how a quantum system becomes a definite observed result remains debated. The Copenhagen interpretation, many worlds interpretation, objective collapse models, pilot wave theory, and relational approaches all try to make sense of the same mathematical success. The experiments work, the predictions work. But the meaning of the measurement remains one of the strange quiet rooms inside physics, with several doors and no universally agreed sign above the exit. Vacuum energy and dark energy deepen the puzzle. Quantum field theory suggests that fields in their lowest energy states should contribute to the energy of empty space. Cosmological observations suggest that space does appear to have something like a small energy density associated with accelerated expansion. But the theoretical estimates and the observed value do not naturally match. The cosmological constant problem is not a minor inconvenience. It is one of the largest mismatches between theory and observation in modern physics, and it may be hinting at something not yet understood about quantum fields, gravity, or space-time. Dark matter is another missing piece. Galaxies rotate as if they contain more mass than visible stars and gas can explain. Gravitational lensing shows extra mass-bending light. The cosmic microwave background and the growth of cosmic structure also point toward dark matter. Yet the particle or particles responsible have not been identified. Underground dark matter searches, space observatories, particle detectors, and collider experiments continue to look for signs of what it might be. The investigation continues across many fronts. CERN and the Large Hadron Collider search for particles and interactions beyond the standard model. Gravitational wave observatories listen for ripples from black holes, neutron stars, and perhaps one day more exotic sources. Underground detectors look for rare dark matter interactions shielded from cosmic rays. Space observatories measure the cosmic microwave background, map galaxies, study supernovae, and test the expansion history of the universe. Each experiment adds another careful piece to the picture. Quantum energy, then, is not a single mystery waiting behind a curtain. It is a network of measured facts, working theories, precise predictions, and unresolved questions. It appears in photons, atoms, fields, the vacuum, nuclei, stars, and the early universe. Some parts are understood with breathtaking accuracy. Others remain open, not because science has failed, but because reality is deeper than the first answers could contain. The hidden quantum energy beneath reality is not a slogan, it is a landscape. Some of it is mapped in extraordinary detail, some of it still lies beyond the edge of present theory, quiet, difficult, and waiting for the next careful question. So the hidden quantum energy beneath reality is not a secret force glowing behind the universe, or a mysterious fuel waiting to be harvested from the shadows. It is something quieter, stricter, and more astonishing. It is the measurable energy structure of quantum systems, the allowed levels of atoms, the packets of light called photons, the wave-like behavior of matter, the energy held in fields, the subtle activity of the vacuum, the mass-giving presence of the Higgs field, the binding energy inside atomic nuclei, and perhaps even the energy associated with space itself. The journey begins in the familiar world, where energy seems smooth. A ball rolls, a fire warms a room, water turns a wheel, planets move through space, and classical physics describes much of it beautifully. But when physicists looked more closely at heat and light, the smooth picture began to crack. The blackbody problem forced Max Planck to propose that energy could be exchanged in small packets. Albert Einstein then showed that light itself could behave as though it arrived in individual photons. What had seemed like a continuous stream was, in certain situations, more like a hidden staircase. That same staircase appeared inside atoms. Electrons did not simply possess any energy they liked. They occupied allowed energy levels, releasing or absorbing photons when they moved between them. Matter waves and wave functions then revealed that electrons were not tiny planets circling nuclei, but quantum systems shaped by probability, uncertainty, and permitted patterns. From those patterns came the structure of atoms, and from atoms came chemistry. Quantum energy is therefore not far away. It is in the periodic table. It is in carbon, oxygen, iron, gold, water, salt, proteins, DNA, and the molecular machinery of life. It is in solids, where energy bands decide whether a material becomes a conductor, an insulator, or a semiconductor. It is in silicon chips, light-emitting diodes, lasers, solar cells, cameras, and the quiet electronics of daily life. Then the picture reaches deeper still. Quantum fields show that particles are not simply hard little dots moving through emptiness, but excitations of underlying fields. The electromagnetic field carries light. The quantum vacuum, though often called empty space, is the lowest energy state of fields that remain present, even when ordinary particles are absent. The Lamb shift shows that this vacuum can leave delicate fingerprints on the energy levels of hydrogen. The Higgs field shows that even mass, one of the most solid feeling properties in nature, partly depends on invisible field structure. Inside the atomic nucleus, binding energy holds protons and neutrons together. Nuclear fusion powers stars. Nuclear fission releases energy by splitting heavy nuclei. Quantum tunneling allows particles to pass through energy barriers that classical physics would forbid, helping alpha particles escape nuclei and allowing the sun to shine steadily across billions of years. And on the larger scales, quantum energy reaches into cosmology. In the early universe, energy, particles, antiparticles, and fields transformed into one another under extreme conditions. Tiny quantum fluctuations may have helped seed the structure of galaxies. Dark energy, though still not fully understood, raises the possibility that the energy of space itself may influence the fate of the universe. So the hiddenness is not because quantum energy is imaginary, it is hidden because it is subtle. its effects are often too small, too fast, too deeply embedded, or too finely woven into matter for ordinary senses to notice directly. Yet those effects are real enough to measure, powerful enough to shape atoms, and precise enough to build the world. The familiar universe is stable not because it is simple, but because hidden quantum rules give it structure. Beneath the calm surface of matter, light, chemistry, stars and space, reality is quietly arranged by energies too small to see and too important to ignore.